Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present and future is the mission of Eco-Environment and Health. Eco-Environment and Health is a journal initiated by prestigious scientists with a strong editorial board including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design and broadcasting. The experts will accompany you like an harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision-making that deeply integrates informatics, ecology and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
Hello, Professor Castel.
Hello.
Hello. How are you?
Yeah, I'm fine.
Yeah,
So
actually,
it's quite funny to realize to make to give a lecture for people sitting 6,000 to 7,000 kilometers away.
yeah, yes.
But this is a follow-up of Corona.
Yes, yes. Actually, you know, I have been to live there.
Yes.
Like I think in 2016, I think it's a PTS meeting.
Ah, okay, yeah.
I do not remember exactly the year, but I really
But it
enjoyed
must be 2016, I guess. Yes.
Yeah, probably.
Yeah.
It's a very nice place.
Mm-hmm. Yeah.
Yeah, because Jerome, he has some meeting today, so he cannot attend.
I guess he's getting more and more busy.
Mm-hmm. Yeah,
Yeah.
sure.
Yeah.
Mm-hmm. Thank you for your support.
Okay.
Mm-hmm.
Yeah. Should I start sharing the screen?
Yeah, you can. Yeah, first of all, I just make some brief introduction of yourself.
Okay.
So yeah, but you can start sharing the screen. That's fine.
Yeah.
Mm-hmm. Thank you. So I think it's almost the time, so we can start.
Yeah.
First of all, I'd like to give a brief introduction of Professor Kester. Professor Kester is the head of Department of Environmental Biotechnology, and he is also the professor of Helmholtz Center for Environmental Research. His research interests including the compound turnover in the environment catalyzed by microorganisms. His current research topics include bioremediation processes, microbial degradation potentials and in situ activity, metabolic flow in environmental system, carbon and nitrogen turnover in soil, genesis of soil organic matter, chemical and microbial ecology in soils, sediments, and groundwater, and also the isotope truth and trace compound. It's like Professor G did. And also Dr. Kester has published more than 150 papers in water research, Stoughton, SBB, and other international journals. His H index is 49 in Scopus. Today, Dr. Kester will talk something about non-extractable residues from environmental relevant chemicals, state of the art and development. Thank you.
Okay, thanks for the introduction. I hope you can see everything.
Yes, no problem.
Okay, yeah, so I'm going to talk about non-extractable residues from environmental relevant chemicals, because this is a very important issue regarding risk assessment and general fate assessment of chemicals in the environment. So chemicals in the environment, they enter the system dominantly terrestrial ecosystems. They have impact on plants, soils, freshwater, and so on. But if we consider environmental relevant chemicals in numbers, then we have to talk about particularly about pesticides, because this is a dominant fraction, and the turnover of these compounds is always depending on the water content, pH value, clay content, and the general environmental condition. And fate assessment is typically done with isotope labeled compounds, and then mineralization, the fate of the parent compound is analyzed. But due to the isotope label, also non-extractable residues can be identified. So if we consider pesticides as one of the dominant component class, we have to realize that China was until 2015 the biggest pesticide user in the world. But overall, you see the number on the right side. There are millions of tons of pesticides applied all over the world in the last decades. And these compounds have a severe impact on the environmental system. So if we consider pesticide, we have a turnover. and particularly also the crop relevant, the food relevant crop plants are impacted by these compounds. Typically they should be protected, but it depends on the general conditions. But there are also residues from these compounds, and they can be found in soils, in sediments, and also in the food plants and fruits and many other compartments. So the original definition of non-extractable residues, or according to the UPAC, is that it's defined as a chemical species originating from these pesticides used according to good agricultural practice, and that are unextracted by methods which do not significantly change the chemical structures. And these non-extractable residues are considered to exclude fragments recycled through metabolic pathways of microbes and other natural systems. So these non-extractable residues are generally formed on all solid media and partially also in freshwater system according to colloidal compounds. So the problem with this definition is that it's not in accordance to the experimental reality. Non-extractable residues include always all possible types, including the natural types, and this makes it very critical to assess. So typically, this fate assessment is done by the application of isotope-labeled compounds, here called substrates, for example, for microbial processes, and then these processes may change the fate of the isotope label from the parent compound. The label may show up in carbon dioxide, in microbial biomass, or just as non-specified residues, for example, in soils or other compartments. But the black box of non-extractable residues is much more complicated than originally considered. For the general assessment of the environmental fate, typically carbon-14 labeled compounds are used. And what is actually considered is that these pesticides by definitions are the parent compound or the metabolites. But according to microbial degradation, it may also be microbial biomass, or even carbon dioxide, or even refixed carbon dioxide after degradation. So the total non-extractable residues are typically all. The risk is associated to parent compounds and primary metabolites, but not to the degraded compounds, and this makes it very difficult, and there's a real mismatch regarding the definition and the experimental access to these compounds. So in principle, we can consider several types of microbes, and the most prominent one and also the highest risk causing is the so-called sequestered type, or let's say type 1. It's sequestered by a reversible binding mode to solid material or even biomass compounds by sorption processes as ionic interactions, hydrogen bonding, and ligand exchange, or even hydrophobic bond. It may be entrapped in pores in this material, and this may cause a very slow desorption or sorption effect. But these kind of compounds are typically a potential risk for the environment. The second type is the really covalently bound residues. And these covalently bound residues may link by ether or carbon-carbon bonds. And they, according to the bonding type, they have different stability. And of course, due to the linkage processes, also the chance of remobilization are much lower than for the just sequestered compounds. And the chemical interaction is driven by these strong binding forces, and many scientists and also many regulatory bodies are considering these compounds are irreversibly or stable associated residues with a low risk for an environment, but actually this needs to be tested. So we can consider these type 1 residues, sorbed or entrapped parent compounds or primary transformation processes, and they are non-covalently linked binding. The second part are these covalently linked compounds, and the stability is much higher than for type 1. But actually, if we consider the all relevant processes, we also may have the label conversion to microbial biomass or biomass in general. And this means an ultimate degradation. And it's just the labeled compounds with no relevance for risk assessment, and also release probabilities are not relevant in this issue. And therefore, it's very important to look at the specific details of these processes. And for that, we have to consider microbial metabolism in soil. And what is typically shown in textbooks is that the parent compounds is somehow mineralized. Do you see my mouse in the picture?
Yes, we can see it.
Okay, yeah. So these compounds are typically mineralized to carbon dioxide and water is often forgotten, and to microbial biomass. But what the textbooks typically are not showing is that biomass and also the compounds may be humified, and these so-called humic substances may be of relevance for the environmental fate assessment. Recent development shows that the term of humic substances is not really targeting the processes in the background. So let's say recent soil scientists often use the term soil organic matter with an open definition to the underlying processes of formation of the soil organic matter. And therefore, we have to consider that microbial biomass is actually contributing to the development of this soil organic matter. So we made experiments. We composted carbon-13 labeled biomass in bioreactors, made the turnover mass balances, and we also applied these stable isotope probing issues for microbial ecology, but I will not talk about this part. We used carbon-13 labeled E. coli, Bacillus subtilis, and also a fungus, Laccaria bicolor, for these composting analysis. And what we found is, in general, that the parent microbes are relatively fast dying and are degraded and turned over. And only 10% of the parent label is remaining within the living microbial food web. Roughly 50% is present as carbon dioxide after 1 year, but 40% of the label on average is remaining in soil, and this must be derived somehow from bio compounds in the system. So we try to visualize these microbial residues in the soil, and this is very, very difficult. It's like searching for a pair of football shoes on a football field, but we managed to find at least some the residuals of dead microbes. And what you can see here in yellow is an empty cell envelope. And you see lots of these patchy fragmented material here covering all the mineral surfaces. And here on the right side, you see already broken cell envelopes. We compared this to systems exposed in groundwater, which can be totally eliminated from biocompounds. Then a certain substrate, in this case toluene, can be applied to these materials, and then microbes are growing on these carrier materials. And what you can see is that this spiderweb material is reflecting the exopolymeric material, which is often found in freshwater systems. And here on the right side, you can see a hyphomicrobian organism growing in that system. And here you already see a fragmented hyphomicrobium cell envelope. And what you clearly see is that these patchy fragments are embedded in these spiderweb materials. And this clearly shows that these materials are accompanying microbial growth in that system. And what is also very important to consider is that these fragments may cause staples, and all the molecules embedded within these staples may be non-accessible to any degradation process. Also, pure cultures are showing these fragmented cell envelopes, but biologists are typically very keen on showing pure microbes. That's why in textbook always microbes are showed in these scanning electron micrographs without these fragments, but all the evidence can be led to the conclusion that presumably these patchy materials in soils are residues from these cell envelopes. And this shows that this organic material in soil is more or less highly similar all over the world, because it's consisting in principle of 4 and 5 types of parent material, which means cell envelopes from gram-negative bacteria, from gram-positive bacteria, from fungi, or even archaea with their different types of cell envelopes. And you can easily consider, if you have fragmented material and you try to assess this porine protein here, then it's necessary that the entire system needs to be degraded. Otherwise, there's no chance for any proteolytic enzyme to degrade these kind of compounds. So the molecular architecture is providing a kind of inherent stabilization processes. If we try to bring this in an ecological context, we can consider that plant material is the primary resource for growing microbes, and as long as the energy and carbon or matter flux is high enough, microbes are happy, they are growing. And in the moment when the flux is ceasing, microbes start starving. And in that moment, if the matter and energy flux is falling below the maintenance needs of these microbes, then the microbes are dying, they are fragmenting, and these residues then are causing soil organic matter. And they are covering all the mineral surfaces, but this material is also a resource for the next growth cycle. And this growth and decay cycle is perhaps one of the most important cycles for the development of soil organic matter. If we now consider the same process for environmental chemicals, because many of environmental relevant chemicals can be degraded by microbes, we may have the same processes, but if we have the isotope label here, then we are getting so-called biogenic non-extractable residues, which may explain parts of the amounts of observed non-extractable residues in the environment. So This microbial biomass contribution may be relevant, and I will show you in the next slides the very detail. But first, I also will focus on the carbon dioxide. If a labeled pesticide is degraded, we have also labeled carbon dioxide after degradation, and the fate of this carbon dioxide may be very, very different. So, very old experiments I did in the last century with the degradation of the polyaromatic hydrocarbon compound of anthracene, and this anthracene was labeled in the 9th position. And from textbook it was known that the 9th position is exclusively going to carbon dioxide during microbial degradation. And therefore, we were not expecting to find any non-extractable residues in soil organic matter. But actually what we found is that roughly 20% of the label were derived from the radio label of the anthracene. So it was a mismatch, it was a contradiction. And therefore, we applied an experiment where we applied the same amount of anthracene without label, but added the same amount of carbon-14 labeled carbon dioxide to the system. And finally, we end up with the same amount of non-extractable residues. And this was a very strong indication that even carbon dioxide refixation may cause these kind of residues. So we made additional experiments with carbon-14 and carbon-13 labeled carbon dioxide, and what we found, it's a matter of carbon dioxide fixation in living soil because death or fumigated soil were not incorporating these compounds into the organic matter fraction. And what we found is that between 0.5 and 3.3% of the net respiration is actually carbon dioxide fixation. And the dominating amount of labeled carbon is found in organic materials, and only a few percent were found as carbonate. So these compounds were, this label was found in compounds like fatty acids, amino sugars, and what we could clearly show, it's a heterotrophic carbon dioxide fixation. So we analyzed the label enrichment in various biogenic amino acids. And what we saw is that aspartate clearly showed the highest label incorporation, and this was the only chance by heterotrophic carbon dioxide fixation. Then we found indication that also orthotrophic pathways contributed, and this label directly ends up in serine and glycine, but to a much lower extent. And other amino acid label incorporation may be indicative for both ways. And what we clearly found was that this carbon dioxide was incorporated in the heterotrophic carbon dioxide fixation of phosphoenol pyruvate and pyruvate ending in oxaloacetate, and from oxaloacetate this aspartate label is primary showing up. And this clearly shows that all heterotrophic organisms are incorporating to a certain extent carbon dioxide via this heterotrophic carbon dioxide fixation. And even humans are derived from atmospheric carbon dioxide in the extent between 5 to 10% of the body carbon. Okay, let's go back to the fate assessment after this excursion to the carbon dioxide fixation. We made these fate assessments with carbon-13 labeled pesticides, here 2,4-D, or metamitron, glyphosate, or bentazone. And bentazone and glyphosate were also applied in a mixed label. They have carbon 13 label and nitrogen 15 label, but I will come to this later. And the typically environmental simulation experiments are the OECD 307 system. These are standard protocols for evaluating the fate of these compounds in soil, or with the OECD 308, the assessment of the environmental fate in water sediment mixtures. And then we analyzed the products formed from this turnover by various analytical procedures. We also analyzed the non-extractable residues in total and try to identify these biogenic residues in terms of label incorporation into amino acids or phospholipid fatty acids. So what we found, for example, with the glyphosate, we have a relatively fast degradation also for metamitron. And due to the fact that the sensitivity of the analysis is much less high than for carbon 14, we always need to test the same process with a low concentration, because typically in the OECD test, compounds were tested in the range up to 2 or 3 milligrams, but for the fate assessment in the residues, we actually need to apply a much higher amount. And what you can actually see is with the low concentration, mineralization starts a bit earlier and with a slightly faster turnover, but in principle, the processes are quite similar. What can also be seen in these water sediment analysis, that in the water body, nothing happens. So the relevant turnover processes are always associated to the sediment phase. So we can consider that in these OECD tests, the sediments always play a key role in degradation. And this is presumably due to the higher amount of microbial biomass in the sediment. And if we look at the turnover of 2,4-D in soil, what we saw is that roughly 50% were finally mineralized. The 2,4-D was no longer extractable after 7 to 8 days. As parent compounds, we found a certain amount of metabolites like dichlorophenol. Oh, sorry, I have to. Okay, yeah. And we had a certain amount of total non-extractable residues in these mass balances. And the question is now, what is the background of these extractable unknown compounds or total non-extractable residues? So if we then added the analysis of the microbial amino acid, I'm sorry for that. Just a minute. Okay. I'm sorry, I cannot stop this telephone ringing. So if we added the analysis of the amino acids, then okay, so if we then start to analyze the label incorporation into the amino acids, then we found that lots of label incorporation was detected in the amino acids. And considering the fact that microbial proteins are 50% of the total amount of microbial biomass, we can simply double the amount of label identified in proteins, and we can consider that at least for 2,4-D in soil, the non-extractable residues are dominantly consisting of these so-called biogenic residues. If we look at the metametron, we have similar effects. We have a relative rapid degradation or mineralization in the soil system, slightly lower mineralization in the water sediment system. The metametron is not detectable after roughly 15 days in the soil, but it's quite long detectable in the water sediment system up to 70 and 80 days. And we have the development of these non-extractable residues. But in soil system, the dominant background of the mass balance is that it's caused by biogenic residues, whereas in water sediment, only 2/3 of the non-extractable residues are actually biogenic. With the glyphosate, we have similar effects, but what we can clearly see is that we have the development of metabolites, and the metabolite formation is even higher in the water sediment system. And here the compound amino methylphosphonic acid is the relevant metabolite. And this is very interesting because in principle glyphosate is easily degradable, and due to the fact that the label compound is also incorporated into the microbial biomass, the question remains, why the hell is this metabolite enriching over the incubation procedure? But I will come to that later. We applied for glyphosate also the nitrogen 15 label, so that we have two different labels in the experiment. And what we can see is that the mass balance of the nitrogen is showing that roughly 50% of the nitrogen is ending up in these biomass residues, and the other 50% were ending in AMPA, so ending in the metabolite. And this clearly shows that the nitrogen is going to a much higher extent to the metabolite and into the biomass residues as it was found for the carbon-13 label. And this was quite interesting. And due to the fact that the metabolism of glyphosate is in principle known in very detail, we could analyze these processes in very detail. So we had very different fate of these compounds between soil and sediments, but in both cases the dominating effect is that nitrogen is distributed between the metabolite and the biomass. Then we followed also the label incorporation into the amino acids, at first in the water sediment system. And what you can see, we have an increase in the carbon-13 label over time and a quite similar increase of the nitrogen 15 label. So nitrogen turnover is going into glycine in carbon-13, but not in nitrogen 15. The nitrogen 15 content in glycine is decreasing over time. And this is an indication that in principle the label is splitted via metabolism. And regarding these effects in soil, we could saw this directly, that the decrease in label incorporation for carbon-13 was observed. And after a slight decrease, an increase again was observed for the nitrogen-15 label. And this is clearly indicating that AMPA has, the development of the metabolite AMPA has something to do between, with the stoichiometry of the different label of carbon and nitrogen in these compounds. And if we look at the parent compound, here's the glyphosate molecule, and the green dots are indicating carbon-13, and the red dot is indicating the nitrogen label. And what we could see is that at first, the so-called sarcosine pathway was followed by the microbes. Phosphate was eliminated, the sarcosine compound was degraded to glycine, and there, during that process, we found the link between the carbon-13 label and the nitrogen label in glycine. But at later stages, for example, particularly in soil, the microbes followed the AMPA pathway, and this means the formation of the aminomethylphosphonic acid and glyoxylate. And this indicates that from glyoxylate, glycine can be produced, but in that case, without the nitrogen label. So we could separate these two processes, and this clearly shows that first the degradation via the direct incorporation into biomass is followed by the microbes, and then this, in later stages the AMPA pathways is following up, and therefore we need to consider that there must be some important reason to change these kind of pathways. And what we could conclude from these data at the first step is that going back to these non-extractable residues, we have the so-called type 1 and type 2 residues, which means parent compounds or metabolites. They may cause a much higher risk than all the label incorporation into the living biomass, which then cause the formation of these so-called biogenic residues or type 3 residues. In the last years, nearly all regulating bodies in the world are following this classification of non-extractable residues, and now the regulatory bodies are focusing dominantly on the risk assessment of these type 1 and type 2 residues. Okay, so we need to revisit the non-extractable residues that are known, and here it's a graph from an old review dealing with the 100 most applied pesticides in Europe, and you can see the amount of residues for some compounds very high, nearly 100%, and then decreasing to very low values. And the black bars are always the ranges of the observed differences in these non-extractable residues. But we may also analyze these data sets in terms of ranking according to the mineralization, and then we nearly found no link to the residue formation, and ranking to the residue formation, we nearly found no observable direct relation to the carbon dioxide formation. So from that approach, the only chance was to evaluate the most critical compounds with the highest amount of residue formation, then the medium residue formation, or even the low residue formation with a lower potential for risks. But in terms of modeling, this was quite unsuccessful approach. And then we started to consider, okay, if we have these different processes causing the formation of residues, we may not find structural alerts or even indications for these compounds. We simply have to consider two different processes for these residue formation. And these may be caused by the structural properties of the parent compounds or metabolites in terms of so-called xenobiotic NER formation, or of microbial metabolism in terms of biogenic residue formation. And this clearly results in two modeling approaches. One approach is dealing with the molecule properties, and the other approach is dealing with the energy turnover of the microbes. And this approach was finally successful by applying this turnover formula, total turnover formula for the heterotrophic organism, in which the substrate is oxidized to a product and the biogenically available electrons are then shifted to the respiration process. And this can be very easily written as a summary equation where the energy can be derived from. And if we know the energy content, we can apply different modeling backgrounds in terms of enzymatic turnover and also microbial growth turnover, according to the Michaelis-Menten or Monod equation. And if we then know how much microbial biomass can be produced from a compound, then we can analyze these turnover residues. I will not go into very detail here with this modeling background, but the important thing is that not all electrons that can be derived from an oxidation process can be used by microbes, and therefore this modeling approach, it's called microbial turnover to biomass model, is based on the biologically usable electron transfer, which is mostly different to the total electron transfer from an oxidation process. So we can relate the biomass to the carbon dioxide formed and to the yield coefficient, or the coefficient for the carbon dioxide fixation. And these can also be considered for long terms with the turnover of the microbial biomass in soil organic matter. And from that, we can simply calculate the maximum amount of biogenical residues from a certain compound. This is very simple, and on the homepage of the Danish Technical University, which are our collaborators in that field, there you will find an Excel sheet where you can very simply calculate these potential amount of biogenic residues from a certain compound. And what we observed is that the experimentally determined residue processes are typically in the range of the predicted model values, but there are two compounds where high differences were observed, and this is phenanthine and linurone in that case, but we are currently not able to talk about details of the background for these differences. So we can show that the total amount of non-extractable residues is not really critical. We should subtract the amount of biogenical or potential biogenical residues, and therefore we can make a prioritization for these compounds dominantly causing this xenobiotic NER. And what you can see on the right side here, you can easily assess these compounds with very low potential risk residues and others with a much higher potential. So there's lots of experimental validation need to be done to follow these processes, but this is currently undertaken, and the regulatory bodies are often considering these kind of approaches. So with our partners from the DTU, we developed a degradation model for the turnover of these compounds, and now with the MTB model, we can also apply the maximum bioavailable energy to these compounds, so that we can also make predictions about the kinetics of this turnover. And even including the partitioning effects between water and sediment, so that we are also able to predictively describe these water sediment processes. Okay, but the question still open is why the hell are the microbes producing metabolites from a certain compound when they are able to fully degrade these compounds and produce biomass and carbon dioxide from that. And if we going back to the glyphosate model, we need to consider that we have a CN ratio of 3 in that compound. Typically, microbial biomass has a carbon to nitrogen ratio of 10. And as long as the microbes are degrading these compounds, the isotope, the nitrogen is ending in the microbial biomass. And this may cause an overflow of nitrogen within the cell, and perhaps a kind of detoxification process for the microbes is then shifting to the AMPA pathway to get rid of the excess nitrogen. And we analyzed this with our model, and what we finally found is that the isotope incorporation is only following the direct sarcosine pathway until the elemental ratio of 3, carbon to nitrogen ratio of 3 is reached, and then the AMPA formation started, so that with the background of the isotope label, ratio of the isotope label, we could show that nitrogen overflow may be a critical parameter for the turnover of these compounds having different elements, and then always the stoichiometry of these element ratios in the degraded compounds and the microbial biomass is relevant for these turnover processes. So this was a quite new effect, and it was only possible by applying these different isotope labels, and the different isotope label turnover can also be modeled with these MTB models, so that these kind of processes can also be predicted by applying this model. Currently, we are trying to make similar analysis of other pesticides, in this case bromoxynil, in collaboration with the Bayer company. We are making these mass balances, but we are currently also applying the ecology of these processes by using DNA and protein stable isotope probing of the degrading organisms. So in between the the regulatory bodies approached us to provide a suggestion and discussion paper for the incorporation of the non-extractable residues, non-extractable residues. And this was an application of the European Chemicals Agency. And what we suggested is that total NER had to be divided in these three different groups. The total amount should be subtracted by the biogenic residues, and then we are ending with the most critical residues in terms of risk assessment. So, and to be more operational, the regulatory bodies considered these type 1 sequestered residues as potentially remobilizable, whereas the covalently bound compounds were considered as hardly remobilizable, and these hardly remobilizable are also considered as being of much lower risk potential. Okay, so the European Chemicals Agency finally considered these differentiation into remobilizable and irreversibly bound fractions, and this is the current matter of legislation, at least in Europe. Okay, so the question how to assess this remobilization is you can try to use physical treatment methods, simulation of heavy rain events, feed and thaw cycling, grinding, wet and dry cycling methods, chemical treatment like pH changes, changes in ionic strength, salt water extraction, and even hydrolysis processes, or biological treatments in terms of highly oxidative enzymes like peroxidases, lacases, or for example, the treatment by soil feeding organisms. So there's many options for testing this remobilization, but the guidelines for these testing procedures are still under debate. Okay, what we can conclude that we have these three different types of residues considered with a different type of remobilizability. And this can be predicted by applying this model, and the model implementation is a decision tool for the European Chemicals Agency for assessment of the persistency assessment of chemicals. So it's quite funny to see that our basic research work is directly feeding into European legislation, and I'm sure that also other regulatory bodies will follow this approach. Okay, finally, I have to thank all the colleagues, all the PhD students, collaborators from Danish Technical University and also from the University of Aachen, and of course the funding bodies like EU, German Research Fund, German Environmental Protection Agency, and also the UFZ for funding. And here in the base, you see the background of the related EU projects that are contributing to this type of research. Okay, thank you for your attention. So I'm happy now to take questions. Yeah.
Okay. Okay. Any questions?
So all the attendees are shy to ask questions.
Yeah, they may have some questions. Since we have several platforms for the for this presentation, they're probably from other places too. So
yeah.
So maybe Professor Kaiser, I may ask a question.
Yeah.
Yeah, thank you first of all, thank you very much for your very informative talk. Very interesting. And my question is that because the isotope method is a very, I think it's a powerful and also very accurate method to measure the non-extractable residue, right?
Yeah.
But also it's maybe have a problem with, so I think your presentation, you also mentioned that because depending on the position you label, because sometimes maybe the like the first the like the metabolite during the first metabolite, so this functional group or some labeled part will be released. So how do you determine that? And also when you design the like those, or you synthesize the compound, right? The label compound.
Yeah.
How do you think about that?
Yeah. So it's very simple, because if we apply 100% or nearly 100% isotope labeled compounds, we can detect the labeled compounds by the mass shift in a normal mass spectrometric approach. And if we have very low concentration, then we need to add a second type of analysis. And this is the so-called GC isotope ratio mass spectroscopy. And this is based on the effect that after chromatographic separation, the peaks are combusted, and then only the isotope label in the carbon dioxide was analyzed, or in the nitrogen is analyzed. And so if we have these higher label, we can easily identify the labeled compound and even the labeled metabolized by the isotope shift, which we can see. And if we have low concentration, then we need to combine both methods, one for the determination of the concentration and the second for the determination of the isotope enrichment. And by combining these, we can always identify the fate of the label in the different groups.
Okay, thank you. So I think somebody is asking questions now.
Yeah, okay.
So the question is that, how did you quantify the mineralized part? The mineralization means completely degrade compound into CO2 and water.
Yeah.
Do you measure label CO2 or to reflect value?
We analyzed the labeled carbon dioxide, and this is relatively easy because we can simply put these gas into a mass spec and then see the ratio of 45 to 44.
Okay, thank you. That's the other question. So yeah, another question, maybe like just like a comment, because Professor Rongji, he's doing something with mainly carbon 14 label, but in your group mainly for the carbon 13. So I think the 14 label is more sensitive, right? Is that right?
Yes, because the background is that the compound specific isotope analysis is not developed for carbon 14, but it's highly developed for carbon 13. This was one of the reasons that why we applied the stable isotope analysis. And without this stable isotope analysis, we would never be able to identify the label incorporation into certain metabolites, amino acids, or whatever, because for carbon 14, these methods are not developed.
Okay. Thank you.
Okay.
So that's the other question. So I think now, right now, that's the other place questions. Yeah, still, I think, yeah, probably the, because this is already in the like summer recess, some student may not, in the
Yeah,
listening.
but actually they are encouraged to ask questions.
Yeah.
But perhaps you should even try to encourage them more to ask questions.
Right. Let's see. Maybe we can wait 1 or 2 minutes to see whether people can have some questions. So all the compound is synthesized by your group, right?
Pardon? I didn't
So
get the message.
carbon-13 label or the nitrogen label, the compound is synthesized by a group, right?
No, it's not synthesized by us, but we have certain sources. We know some people that are able to make these special syntheses, and in some cases we also got the labeled compound from the producers.
Right.
So, but as you can see, using dual or even multiple isotope labels may offer very interesting question for analyzing the metabolism of that compounds and also the ecological impact.
Yeah, that's right. Yeah, I also in our group we also did some like isotope research, but it's very expensive.
Yeah, of course. Yes.
Yeah, it's a very interesting topic.
Yeah.
Mm-hmm. So now, maybe another question coming. So the question is that, are the experiments done with 100% fully labeled compound? So only part of the label, only part of the compound is unlabeled. So like 20% or 40%.
Yeah, so typically it's very difficult to reach 100% isotope label, but we always try to have more than 95%, and typically we are able to obtain these kind of isotope purity.
Okay.
Yeah.
Okay. I think, thank you, Professor Kastner. Thank you very much for your very wonderful presentation. Hopefully, you can visit Nanjing after the pandemic.
Yeah. So let's see what the future is bringing. I'm always interested in traveling, and perhaps you know that I was already several times in Nanjing for giving lectures. Not online, but in face-to-face meetings.
That's better.
Yeah, that's better, but times are changing due to Corona.
Yes. Thank you again. All right.
Yeah. Okay, thanks and goodbye. And if you have any questions, just send an email.
Sure. Okay. All right. Thank you very much.
Okay, thanks. Bye.
Bye-bye.